Friends, now we will be discussing about the resonance circuit. And actually there are two types of resonance circuits. One is series resonance and another is parallel resonance circuit. So first we are going to discuss about the series resonance circuit. So series resonance circuit is a simple LCR circuit in which inductor, capacitor and resistors are connected in series. Actually, in last time also we discussed about such a circuit, and we know that in that circuit there are certain conditions in which the current becomes maximum. Okay, so I'll be discussing that with you. But before that, I just want to know that what is resonance. You must have studied in 11th standard also that every object has its natural frequency of oscillation. Every object. Now what happens that when the frequency of the applied force becomes equal to the natural frequency of the oscillating body, then because of that the amplitude of the oscillations suddenly becomes maximum, and this is called resonance. Okay, so here we are talking in context of electrical resonance, okay, and that we are going to discuss. Now, as you know that in a series resonance circuit, actually they are talking about series LCR circuit. When they talk about the series LCR circuit, we know this thing that the expression for impedance is given by Z is equals to under the root R square plus XL minus XC whole square. Okay, now you also know this that the current is given by V upon Z, and Z is given by V upon under the root of R square plus XL minus XC whole square. Fine. Now you have to understand this that the current would be maximum when Z is minimum. When Z is minimum. And for Z to be minimum, the same thing is that XL minus XC should be 0, and this implies XL should be equal to XT, and this implies omega RL should be equal to 1 upon omega RC, and this implies omega R square should be equal to 1 upon LC, or omega R equals to 1 upon root LC. You know this omega R is 2 pi nu R, so you can write nu R is equal to 1 upon 2 pi root LC, and this is how you can find the expression for resonance frequency. Okay, and for this particular resonance frequency, current would be maximum, or at this omega R is equals to 1 upon root LC, current would be maximum. Now, why current would be maximum? Because at this particular frequency Z would be minimum, and what will be the value of Z? That minimum Z would be equal to capital R. Okay. Now we will try to understand this with the help of a graph. Okay, so for this we are plotting a graph now. I hope that you understood this and written it. Now you try to understand if we plot a graph here. So this graph would look like this. We are plotting a graph between maximum value of the current, that is I naught I naught and omega frequency. Now when we are doing this, see what happens that graph pattern is actually like this. And that we are plotting for different values of R. Okay, so first we are plotting for a value of R when value of resistance is actually 100 ohm. Excuse me. And next we are plotting for another one in which the value of R is 10 ohm. Here value of capital R resistance is 10 ohm. So for these two different values we are plotting a graph, and one thing is common here, and that thing is that for a particular value of frequency the value of current becomes maximum. So this particular value of frequency is omega r. That is the resonance frequency. So doesn't matter what is the value of the resistance, but for a particular value of angular frequency, the current would be maximum. Okay. Also, one more thing you have to do here is that we know this, that RMS value of the current is this is the peak value actually. So RMS value of the current is given by IV, and IV, we know that IV is equals to I naught by root 2. So IV is equal to I naught by root 2, and if I extend it like this, and then I get two frequencies corresponding to this value, and these two frequencies are I am plotting here. These two frequencies are actually omega 1 and omega 2. They are falling, and omega r is falling in between them. Okay, so this is omega 1, this is omega 2. Okay, and this is omega, which we are plotting on x-axis. Okay, so you can see that for a particular frequency omega r, value of current becomes maximum. And it is obvious that as you decrease the resistance, the peak value of current would be more. If you increase the resistance, peak value of the current for that circuit would be less. Okay, so this is what the graph is. Now, what this graph implies is that for a particular frequency, the circuit responds. And how does it respond? By giving the maximum current. Okay, so for this particular frequency omega r, the value of current in for both the resistors, you can see, becomes maximum here also and here also. What does it mean? It means that circuit responds to this particular frequency, and when circuit responds to this particular frequency, the current becomes very high. What does it mean? It means that when the frequency of the applied voltage becomes equal to a particular frequency, then the current becomes maximum. Circuit responds. Now, this type of circuit is said to be acceptor circuit, because it is accepting a particular frequency. So that's why such a circuit is said to be acceptor circuit. It is accepting a particular frequency. Now, this type of acceptor circuit, you must have noticed this thing, that suppose that radio sets are there, and if you want to play a radio station whose frequency is particular frequency, say 93.4 FM. Now, if you want to play this 93.4 FM, so you change the rotate the knob of that, and when you do that, actually the variable capacitor changes its frequency, and it sets its frequency, the radio set sets its frequency according to the frequency of the waves which are reaching. When the frequency of the radio set becomes equal to the frequency of the wave which are reaching, then what happens? That resonance oscillations occur, resonance takes place, and the current in the circuit becomes maximum. So this is how the acceptor circuit works. So these types of circuit which are based on this, they are called acceptor circuits. So they are actually accepting a particular frequency. So this is for series LCR circuit. And this is what the series resonance is. Friends, now we will try to understand the quality factor, which is denoted by capital Q, or it also gives us the idea about the sharpness of the resonance. Now you try to understand this, that quality factor Q is defined as VL upon VR or VC upon VR. Now what is VL, VC and VR? That is obvious. That VL is the potential difference across the inductor, VR is the potential difference across the resistor, and VC is the potential difference across the capacitor. Okay, now by both the formulas we can find the value of quality factor. You can see that Q equals to VL upon VR. Now you know that VL is I naught XL and it is I naught R. so it is cancelled. Now XL, you know this, that XL is omega L upon R. Okay, and omega L or omega R also you can write that omega R is the resonance frequency. You know that resonance frequency is given by 1 upon 2 pi root LC, and here into R, and in denominator L is there, so it is L by R. Now you know this, that it is 1 upon 2 pi, and this and this will cancel, but what is left is root L. So 1 upon 2 pi root L by R is the quality factors formula by the VL upon VR. Similarly, you can find it by VC upon VR also. If you will try to find it by VC upon VR, let us try to do that. VC upon VR. So if you do this, you will be finding it like this. Q is equals to VC will give you I naught XC. Just a minute. One mistake we did. Actually, in this previous one, there is one problem. So I am not solving it just now. See here first. The mistake what we did is I am correcting it here. VL is I naught XL, VR is I naught R. That is correct. Now omega R into L upon R. See, after this, you have to understand is that omega R. Actually, I did it wrong. Omega R, value of omega R is equal to 1 upon root LC. It's not 1 upon 2 pi, it's 1 upon root LC, sorry. Now what you have to do, you have to substitute it. It is 1 upon root LC multiplied by L by R. So when you do this, 1 upon R will come here. Okay, and this root L and L will cancel. So what you will get is root L by C. This is Q, the quality factor. Okay, similarly you can write it for this. If you do it for VC, you see Q is equals to VC. VC is I naught XC and upon I naught R. XC is given by I naught. I naught is cancelled. So XC is 1 upon omega C. So you can write it like this. It is equals to 1 upon omega R C. Okay, and R is here written. So now you can substitute omega R, which is 1 upon root LC. So omega R is 1 upon root LC, so it will go up. So it is root LC divided by RC. Now C and root C is there, so that will be cancelled and root C will remain. Okay, so you will get, if you solve this, you will be getting this only, that is 1 upon R root L upon C. This is the expression for quality factor.